squared. And these are the commands, the R commands for computing the PDF and the CDF of a chi-square distribution. And these are percentiles of a chi-square distribution. And this will be useful later. And I showed you a table. Didn't I? Oh, I showed you a table which can be used to read these values. So these are values such that the probability that a chi-squared variable is less than or equal to this is alpha. And you can read these values from a table, which I showed you, which is, you should have the table, guys, in one of the handouts. Okay? And these are some properties of a chi-squared variable. The first one is the expectation, the variance. And this property, number 3, explains why chi-squared is a sampling distribution. That's because you have a function of the data on the left-hand side, which involves only the data, and it has a chi-square distribution. That's precisely why chi-square distribution is a sampling distribution, right? And these are some more properties of the chi-square distribution, and I did an example. This is the example I did on Tuesday. Then I went to the student's t distribution, which is defined by this PDF. The student's t distribution is due to a British statistician named Bill Gossett. He worked for the Irish company Guinness, and because the policies of the company is that you are not allowed to publish your own research in the public domain, so he published it under the name student. Right? You know what I'm saying? So that's why it became known as the student's t distribution, right? This is a typical shape of a student t PDF, and it compares to the normal PDF. The only difference is in the tails, where they decay to 0. And these are R commands for computing the PDF and the CDF of a student's t, right? Okay, so now let me finish this one. The next thing I'm going to talk about is percentiles of a student t variable t, right? So this guy is known as the alphath percentile. So the alphath percentile of a t variable is the value for which the probability that a t variable is less than or equal to that is alpha. So for example, let's take an example. Suppose you want to read t, say 0.95 at a equal to 1, right? And there is a table. You should look in the handout I gave you at the beginning. There's a table for reading this. Hopefully it is here. Oh, here it is. Okay. There's a table for reading this gap. And let me put this over here. See it better. Now, to read this gap, all you have to do is read along the first row, which is 0.95, and along the first column, 1 So the value will be 6.314. Right? So what this implies is that a t variable with 1 degree of freedom less than or equal to 6.314 is equal to 0.95. You follow me? Yeah? It's easy to read. It just you use that table which I gave you at the beginning. If you don't have a copy of this handout, see me after the class, okay? I've got enough handouts. Say, suppose you want to read t at right? So this alpha is 0.01, a is equal to 10. Because t is a symmetric distribution, remember on Tuesday I drew a picture of the t density, which is symmetric just like the normal density, right? So this, because of symmetry, that this guy here is the same as minus t, right, by symmetry. Remember the picture that I drew on Tuesday, guys, okay? Because of the symmetry, this is the same as this, right? And this guy here, this we can read. So all you have to do is go here, this is 0.99, and 10 is over here, so the value is 2.764. So the value will be minus 2.764. So what this implies is that, guys, the probability that a t variable with 10 degree of freedom is equal to 0.01. Do you follow me? Yeah? So here I have used the symmetry of the t density or the t distribution. So when, okay? Any questions, guys? Don't be afraid to ask me. I'm disappointed that none of you Zoom me. Why is that? All right. So that's the table. Now some other properties. Right, I want to write down some properties of a t variable with no, I mean, you're not expected to know the proofs, but if you want to prove them, that's fine with me. So the first is the expected value is 0. Second is the variance is this, right? The third is that x, which is a t variable, approaches a standard normal variable as a, the parameter a, the degree of freedom parameter, approaches infinity, right? And 4 is the most important one, is the following. X bar, okay, before that, suppose x1 to xn are right, then x bar is the sample mean divided by s divided by square root of n, right? Follows the t distribution with n minus 1 degree of freedom, right? Where x bar is the sample mean, okay? X bar is the sample mean, guys, and S is the sample standard deviation. But I'm going to use I will explain later what I mean by unbiased and biased later on. But you see, I gave you two definitions for S. One is biased, the other one is unbiased, right? So here I'm going to use the unbiased version, which is do you remember this, guys? Or you've already forgot? S is the sample, right? This is the unbiased version I gave you some time ago. Do you remember this? Yeah. Okay. So the thing is that this guy here has a t distribution with n minus 1 degree of freedom. Now the important thing about this is that this result, if I call this, let me call this star, for example, right? The LHS, or the left-hand side of star, is a function of data only. Okay, and the RHS of star the right hand side of star is the t distribution. Yeah? So do you see what I'm trying to say? The left hand side is a function of the data only. The right hand side is the t distribution. Come on, guys. All right, guys. So this is exactly why, because of star, you can see star. I mean, can you see? Yeah. Because of star the star explains why t distribution is a sampling distribution, right? Okay. All right. Let me put this here. All right. Now I'm going to do an example and then move on to an important part of this course. So let me just, first of all, before I example, I mean, I'm sorry, I know I only did one example on Tuesday, but I will try to do more example later on. So don't complain yet, okay? I will try to do more examples. Just a minute. Sorry, I don't like this example. Let me find another one. I really don't like this example. So, okay, let me do another example, okay? I'm sorry. Right? Okay. All right. So this is an example. Shh. So you have a random sample, which IID means independent. And you know what it means? Independent and identically distributed from a normal distribution with 1, 1. And we want to find this probability that x bar is the sample mean minus a 1 is less than s. S is what I wrote down here, guys. Now, how would you do this, guys? So let's start with this, okay? Now, do you remember that one of the properties I gave you for the normal distribution? I mean, we did the normal distribution about a week ago, right? Or is it 2 weeks ago? If x1 to xn is normally distributed, what distribution x bar has? Do you remember or no? You already forgot. Do you remember this? That if x1 to x1, I mean, if you look back in the handwritten notes, you will see this result that if you have a random sample from a normal distribution, then the mean, the sample mean also has the normal distribution with parameters mu and sigma squared divided by n. That's one of the results, right? Come on, guys, just try to read what I gave you, guys, please. Okay. Now, this you can write as all right, this is, I don't know whether you followed what I did, but this is the answer. By property 4, which is over here, that this guy here has a t distribution with n minus 1 degree of freedom. So that's what I have used in the last step, that because on the top you have the normal with 0 mean and 1 over n variance, which is what this will have, because here you are assuming that x1 to xn are IID normal with 0 mean and sigma squared variance. So x bar will have a normal distribution with 0 mean and variance sigma squared by n. Right? Okay, so this is in the form of the left-hand side of star. So you can use property 4 and say that this is equal to this. Is that clear or no? Are you lost? Do you see what I've done? I have used star. Basically, I have used the result of star to get from this line to this line. Okay? All right. If you don't follow what I did, just see me after the class, guys. Okay? All right. Now I'm going to move on to an important part of this course, which is called the following. So we are done with sampling distributions. The next part I'm going to talk about is point estimation. This is a really, really important. I mean, this is where the course will get interesting, hopefully. Point estimation is really important part of statistics, right? So consider the following example, right? The example is, okay, you have a population which is equal to all men in the UK. And we denote the population by this symbol here, you may remember, you may recall. And we have a parameter theta. This is a parameter. And we are interested in knowing the average height of we are interested in knowing the average height of all men in the UK, which is impossible to calculate because there are millions of men in the UK, right? So you can't possibly calculate the value for theta, right? So what you need to do, you need to draw a sample which is accessible. So let's draw a sample S. S denotes the sample. Suppose I select Suppose I select 3 men randomly selected from the UK, right? And you can estimate theta hat is an estimate of theta. Right? So theta hat is an estimate of theta based on the sample S. So you select 3 people, right? And you measure their heights, right? So let's suppose x1 is the height right, and x2 is the height of the second, and x3 is the height of the third. Okay, so you select 3 people and measure their heights, right? And we want to estimate theta hat, which is we want to find what theta hat is, right? Which is an estimate of theta. Now the question is, how can you do it? The question is, what are the possible estimates for theta? I mean, how can you estimate, how can you calculate theta hat? How can you calculate theta hat? You have 3 people and you have 3 measurements, right? The 3 measurements are the heights of the 3 people. And we want to know how to calculate theta hat. One way is to do the following. Okay, one way, let me call it theta 1 hat, is to sum the 3 heights and divide by 3. So this is an average height of the 3 people. But this is not the only way to do it, is it? I mean, this is not the only way to estimate. This is not the only way to estimate. What about this? This is another way to estimate theta, right? Or what about this? This is another way to estimate theta. And what about this one? This is another way to estimate theta, right? So there are possibly, I mean, many different ways you can estimate theta. The question is, which one is the best estimate? So the question is, which of these is the best estimator for theta, right? Because you can possibly have many different. Now, to answer this question, I'm going to introduce the following. I'm going to introduce two criteria. Number one, I'm going to introduce 2 criteria to determine which is the best estimator. Number one is known as the bias. Okay, before I do that, okay, suppose theta hat is an estimator of theta. Okay, then the bias of theta hat is defined as this, right? And number 2 is the MSC. MSC stands for, I will explain in a minute. It stands for mean squared error. Okay, it's the mean squared error, right? And is defined as the following. It's defined as theta hat minus theta squared. Right? So there are 2 criteria to determine which of the estimators is better, right? So I'm going to say the following. The smaller the the smaller the bias, the better the estimator. And the same thing with MSC. The smaller the MSC, the better the estimator, right? All right, guys, are you with me so far? Right, now, okay. Suppose theta 1 hat and theta 2 hat are estimators of theta. Okay. Suppose you have two. I mean, in practice you can have more than two, but for simplicity, let's say you have two estimators for theta, right? In this case, you will of these two, you would select theta 1 as the better estimator, if if the absolute value of the bias of theta 1 hat is less than the absolute value of the bias of theta 2 hat, all right? And the other way, if it is the other way around, you will select theta 2, right? And you will select I forgot to say, okay, let me write this first. Right. You select theta 1 hat as the better estimator of the two if MSC of theta 1 hat is less than MSC of theta 2 hat. And I should have said here that with respect to bias, right? So this is with respect to bias, this is with respect to MSC, okay? You follow me, okay? Next thing, I need to define a few things. So this is where the definitions come in. So some definitions. Number one is the estimator theta hat is unbiased for theta if the bias of theta hat is 0. Okay, so this is a good thing because the smallest value you can have for bias is 0. Okay, so if the bias of an estimator is 0, then that's a really good estimator. Okay, and number two, theta hat is asymptotically unbiased for theta if the limit as n goes to infinity of is 0. So if the limit of this, as n is the sample size of the random sample, approaches infinity, this is 0. So this is once again a good thing. But this is not as good as the number 1, which is unbiasedness. And number 3 is the following. Theta hat is consistent for theta. So the key words here are these ones. This is a key word: unbiasedness, asymptotically unbiasedness, and consistency. Right? It's consistent for theta if the limit all right. Once again, the MSC, the smallest value the MSC can take is 0. Right? So if MSC is 0, then that's a good thing. But it can never be 0. In practice, MSC can never be 0. So if the limit is 0, that's once again a good thing. Right? So all these 3 properties are properties of a good estimator: unbiasedness, asymptotically unbiasedness, and consistency. Right? Okay. I will do some examples later on, but before that, I need to prove some properties. I know, do you guys like proofs? You must have done proofs in your real analysis or whatever. Yeah. So I need to prove some properties. Okay. This is where properties comes in. Properties. Number 1 is the MSC of theta hat is equal to the variance of theta hat plus the square of the bias. Number 2, variance, excuse me. All right, this is number 2. Number 3 is the following, that if the expected value of theta hat is k, a constant, then all right, so these are 3 properties. I will prove them in a minute. If I have time, I will prove them today. If I don't have time, I will prove them next time. But let me see if I can prove at least one of them. Right, so this is proof of property 1. Okay, so I'm going to start with the left hand side, which is the MSC of theta hat, which is the expectation of theta hat minus theta squared. Right? Now I need to prove that this is equal to the right hand side. Okay, so to do that, you see what I've done? I have subtracted this term and added the term, so I haven't changed anything. Okay, so but I'm going to put rounds. I'm going to put brackets around these two. Right now, I'm going to use the formula that a plus b squared is a. So I'm using the formula to get this. All right, this is using the formula that a plus b squared is a squared plus b squared plus 2ab. Right. Now I'm going to take the expectation inside, so you have this is the first term, right? And the second term is this, right? And the third term is 2 times right. Now let me ask you, what is this first term here? Do you know this? What is the first term? The first term is the variance. Come on, guys. The first term is the same as the variance. Remember this, that if you have the variance of a variable x, right, is defined as the expectation of x minus the expectation of x squared, right? So this is what I have used. So what you have here is exactly the variance of theta hat because of the definition of variance, right? Now the second term, what expectation of theta hat minus theta is, I just defined a minute ago. What's that? Is the bias. It's the bias of theta hat squared, right? That's this term here is a bias, as I just defined 1 minute ago. Now for the third term, I'm going to take the expectation inside, but this guy here is a constant. This guy is a constant. This is a constant, so you can pull it outside. So this becomes 2 okay? All right. Are you with me? Right? So this becomes the variance of theta hat. Now the bias of theta hat is a constant. So the expectation of a constant is itself. Okay, so this becomes right. Now here I'm going to take the expectation inside the brackets, the square brackets, right? So you get 2 expectation of theta hat minus the expectation of theta hat. Now the expectation of theta hat is the expectation of theta hat, because the expectation of theta hat is a fixed number, right? So the second expectation is simply the expectation of a constant, which is itself. So this guy here is equal to 0. Okay? Do you follow me? Because the expectation of theta hat is a constant, and the second expectation, taking the constant, the expectation of a constant is itself. So we have proved that this is equal to the right hand side. That's what we wanted to prove. Right? Is that clear, guys, or not? Or are you lost? It's not as hard as the algebra we've done. The analysis we've done. All right, now that's property 1. Property 2. Property 2, if I have time, is easy to prove. Or maybe I will prove it now, so that, okay, this is, just bear with me, guys. You have time for lunch. Proof of property 2. Property 2 is really easy to prove, because you see the property 2 is this one here. Theta hat is consistent, right? Theta hat is consistent if and only if, this means if and only if, the limit of MSC is 0. Okay? Now this is if and only if the limit of the all right, this is by property 1. All right. Now, because both these are positive numbers, this implies that the limit of the variance of theta hat must be 0, and the limit of the square of the bias must be 0 too. All right, and finally, this happens if and only if the limit of the variance of theta hat is 0, and the limit of the bias theta hat must be 0. All right. So that proves property 2, and we are nearly done, I think. So there's only property 3 left to prove, which I will do next time. And after that, I will do lots of examples, guys. All right. Is this proof clear or not? It just, any questions? Just let me know, guys. Come on, tell others that I'm not on strike. I don't know why some of you guys are on strike today. I don't know why. Yeah? Yes.
How can we guess theta here? How can we go?
Theta is unknown. Theta is unknown parameter. You can't estimate theta. You don't know the exact value for theta because the population is so large.
Yeah, so if we don't know that, how can we calculate
You can't calculate exactly, but you can calculate this part. So you don't know how to calculate this, but you can calculate this one. Yeah. I will show you in the examples I will do next week how to do that. Yeah. Hi. You done? You guys okay? Yeah, good. Any questions, just come and see me, okay? Yeah, good. Yeah. Hello, sir. You okay?
Yeah, I just think I'm allowed.
See, we will do examples next week on this. I haven't had time to do examples today.
So do you know where the supervision, the capital class today?
Yeah, today is in G, which one are you going to?
Today.
1 to 2 or 12 to 1? Which one are you going?
1 to 2.
1 to 2 is in G207 in Alan Turing, ATB.
207.
207, yeah, G207.